Imagine carrying a device with access to, like, the sum total of human knowledge, but when you ask it to recall a nuanced conversation from Tuesday, it just gaslights you.
Oh, yeah. It is the absolute worst.
Right. Like you might tell your AI agent on Monday that you are newly allergic to dairy, and then by Thursday, it's enthusiastically recommending a cheese tasting tour in your city.
Yep. It's incredibly frustrating when a seemingly brilliant system completely forgets the context you just established a few days ago.
Okay, let's unpack this, because when you rely on these tools to manage your complex projects or your research or just your daily workflow, this goldfish memory is a massive bottleneck.
A total bottleneck, yeah.
It strips away that whole illusion of an intelligent assistant. It leaves you feeling like you're constantly starting from scratch, typing out the exact same parameters over and over again.
And solving that specific bottleneck is actually the mission for today's deep dive.
Yes, it is.
We are looking at a foundational state-of-the-art generative AI paper from May 2026. This comes straight from the researchers at the Vector Institute and the University of Toronto.
Okay, and what's the paper called?
It is titled Goal-Oriented Reasoning for AG-Based Memory in Conversational Agentic LLM Systems.
Quite the mouthful.
It is, yeah. But the core of their research focuses on this amazing new framework called Goal-Mem.
Goal-Mem.
Right. Which essentially cures this goldfish memory problem by teaching AI agents to abandon forward guessing and instead teach them to think backward.
So before we get into thinking backward, we really need to understand why the current system is so deeply flawed. Right now, the standard approach to AI memory relies heavily on semantic similarity within a RAG framework.
Exactly. RAG meaning Retrieval Augmented Generation.
Right. So we feed our chat history into a database, the system maps our prompts to mathematical vectors, and then it looks for a close cosine match in that multidimensional latent space.
Which sounds highly sophisticated.
It does, but under the hood, I mean, it is fundamentally just a giant game of mathematical word association.
That is the perfect way to describe it. It's just word association. Semantic similarity is incredibly powerful for retrieving a specific document if you know the exact keywords, right?
Yeah, like a normal search engine.
Exactly.
Yeah.
But it breaks down completely when you are having an ongoing, evolving dialogue with an AI.
Because it's not a static document.
Right. The current system uses what researchers call forward reasoning. It takes your immediate prompt, converts it into a vector, and just blasts outward into the dark, basically.
Just hoping to hit something.
Hoping to intersect with another vector that points in the same general direction.
So it starts with the prompt and assumes the answer is sitting right next to the words you just typed.
Exactly. And the paper uses this really great running example that illustrates exactly why this forward reasoning falls apart in practice.
Oh, the Alice example, right.
Yeah, let's look at Alice. Imagine a user named Alice. She opens her AI assistant and types a very casual, everyday prompt. She says, "I like the cafe I went to last week. What drink should I try this time?"
Which, to a human, is trivial.
Completely trivial. But let's look at how the standard semantic RGA system processes it. It strips that prompt down to its core vectors, and it heavily weights the keywords cafe and drink.
Because those are the most prominent nouns.
Right. It then blindly searches Alice's memory database for those semantic clusters. So it might pull up an old memory where Alice said, "My favorite drink is Red Bull."
Oh, no.
And then another entirely separate memory where she said, "Lunar Cafe is nice."
I see where this is going.
Yeah. The AI retrieves these two distinct semantic hits, matches them together in its context window, and confidently outputs. I would recommend Red Bull at Lunar Cafe.
That's hilarious. It entirely ignores the constraint of the cafe I went to last week because it is so fixated on the lexical weight of the words drink and cafe.
Exactly. It just grabs the highest scoring vector matches and calls it a day. Or we see an even more frustrating failure mode. Let's say it actually successfully identifies the specific cafe she visited last week, Cafe Momoko.
Okay, so it got the location right.
Right. But looking at the memory log for Cafe Momoko, it only sees that Alice ordered eggs and chicken courage.
Ah, no drink mentioned.
Because the specific word drink doesn't appear anywhere near the vector for Cafe Momoko, the forward reasoning system just hits a dead end.
So what does it tell her?
It flat out tells her, "It seems like you didn't order any drinks at Cafe Momoko."
That is maddening. It's like asking a friend to remember where you left your keys. And instead of mentally retracing your steps and logically ruling out locations based on your routine,
they just panic.
Yeah, they just start frantically shouting out every place you've ever mentioned the word keys in your entire life, like your pocket, a locksmith, the piano.
That is a brilliant analogy.
It is just blind word association masquerading as memory recall.
And relying on that blind word association becomes a catastrophic limitation when you move into multi-hop reasoning.
Multi-hop reasoning. Break that down for us.
So multi-hop questions require the system to connect multiple distinct memories across time to arrive at a single logically sound answer.
Making hops between different memories.
Exactly. The information required to support actual grounded reasoning is rarely sitting directly adjacent to the words you used in your prompt.
Which is exactly how human beings naturally communicate. Like, we don't speak in perfectly formatted query strings.
No, we really don't.
We reference things obliquely. We say, hey, what was that thing we talked about after the movie? We expect the system to make those temporal and logical hops.
And forward reasoning just can't do that.
Right. So if forward guessing based on word association is a dead end for complex questions, how does Goal-Mem reverse the engine?
What's fascinating here is that Goal-Mem completely abandons the vector blasting approach. It introduces a framework rooted in the classical logical principle of backward chaining.
Backward chaining. So starting from the end.
Precisely. Instead of taking Alice's prompt and expanding outward, Goal-Mem treats her question as a final unproven theorem.
Okay.
It looks at the goal, recommend a drink at the cafe I went to last week, and determines that to answer this without hallucinating, it must break the final goal down into smaller atomic sub-goals.
So it sets up a strict logical checklist before it even attempts to search the memory database at all.
Yes, exactly.
Walk us through the specific sub-goals it generates for Alice.
Okay, so the AI realizes it needs to satisfy 3 distinct, verifiable steps. Sub-goal 1, what cafe did Alice actually visit last week?
Makes sense.
Sub-goal 2, what flavor profiles does Alice generally prefer? And sub-goal 3, what drinks containing that specific flavor profile are actually served at the cafe identified in sub-goal 1?
I love that. It establishes the stressful constraints of the problem first. It knows exactly what missing puzzle pieces it needs to find.
Right, it's targeted.
But, I mean, bridging the gap between a strict logical checklist and the messy reality of human conversation seems incredibly difficult.
It is a massive challenge.
Because pure symbolic logic requires strict mathematical rules, but human language is full of slang, typos, and, implicit context.
Exactly. And the researchers solved this tension by formalizing the backward chaining process, using something called natural language logic, or NL logic.
NL logic.
Yeah. It is a brilliant marriage of 2 vastly different paradigms.
Yeah.
On one side, you have old-school first-order logic, which provides strict mathematical guarantees using typed variables.
Okay, and the other side?
On the other side, you have the massive semantic comprehension of a modern large language model.
Oh, wow. So NL logic allows the AI to set up a rigid logical equation, but the variables inside that equation are natural language phrases rather than strict mathematical symbols?
Precisely. The system creates a rule that says variable X must be of type drink.
Okay.
In pure symbolic logic, drink would have to be explicitly defined in a rigid ontology.
A hard-coded list somewhere.
Exactly. But with NL logic, the AI uses its underlying language model to dynamically evaluate if a retrieved phrase like keto latte conceptually fits into the drink variable.
That's incredibly smart.
It is. It leverages the fluid comprehension of conversational English to satisfy the rigid structural requirements of a logical proof.
Here's where it gets really interesting, though. Because formulating the right sub-questions is a massive step forward. But the system still has to mathematically prove that the answers it retrieves from a rambling chat history are actually correct.
Right.
If it just guesses the answers to those sub-goals, we are right back to the hallucination problem.
Which is why verification is the beating heart of the Goal-Mem framework. It uses a core component of NL logic called verifiable unification.
Verifiable unification?
Yes. You can picture it like a detective's corkboard.
Oh, with the red string.
Exactly, the red string. The AI is the lead detective, and it has to perform a series of strict logical checks before it allows any new piece of retrieved memory to be pinned to that board as verified evidence.
Okay, so if the first check is type consistency, making sure the retrieved memory matches the variable type, the AI looks at a retrieved mention of a Kyoto latte and uses its language model to confirm that a Kyoto latte is, in fact, a drink.
Spot on.
And if the memory had returned matcha powder, the AI would instantly reject it because powder is an ingredient, not a drink.
That is the first hurdle cleared. The second check is equality, which ensures consistency across all the existing substitutions.
Right, so it has to cross-reference the new clue with the rest of the corkboard to make sure the red strings don't cross and contradict each other.
Exactly.
So if an earlier sub-goal already established that Alice strongly prefers matcha flavors, and the new memory suggests the cafe serves a great strawberry smoothie,
Well,
the AI evaluates the variables. Strawberry does not equal matcha.
nope.
So the evidence is rejected, preventing a contradictory recommendation.
And that brings us to the final hurdle on the corkboard, logical entailment.
What does that mean in this context?
Well, once all the variables are plugged in Kyoto Latte, matcha flavor, Cafe Momoko, the AI, must evaluate the raw text of the retrieved memory to see if it actually proves the fully grounded statement.
Oh, I see.
Let's say the raw memory reads, Cafe Momoko advertised a Kyoto Latte made with premium matcha powder. The AI acts as a semantic judge.
Okay.
It evaluates the sentence and confirms that, yes, this specific string of text logically entails the fully formed subgoal. Only then is the memory verified and pinned to the board.
I mean, I understand how powerful that verifiable proof is, but I have to push back here on behalf of the listener.
Sure, go for it.
When you introduce terms like backward chaining, verifiable unification, and multi-stage logical checks, the immediate concern is computational efficiency.
Oh, absolutely.
If the AI is meticulously evaluating every variable, doesn't it just endlessly loop and burn through massive amounts of compute tokens? Older methods like React often spiral out of control when they try to chain thoughts together.
That is a critical concern for any engineer looking to implement this at scale. The researchers designed a highly efficient mechanism specifically to prevent infinite loops. They call it the depth loop.
The depth loop, how does that work?
To understand it, we need to clarify how the system searches. When the AI hits a wall, for example, it is trying to verify the cafe Alice visited last week, but the retrieved memory simply says she went to Cafe Momoko without specifying the date. The AI does not blindly search the entire database again.
Right, because that would waste tokens. It has to refine the search. So it can either search wider, which would be a breadth step, or search deeper, which would be a depth step.
Exactly. In a breadth step, the AI realizes its initial logical decomposition was completely wrong, and it reformulates the goal entirely.
Okay.
But in a depth step, it keeps the goal and generates a highly targeted query specifically for the missing piece of information. It creates a new antecedent.
I see.
It says, I know she went to Momoko. Now let me search explicitly for any date or time associated with her visits to Momoko.
So it collapses the search space immediately. It only searches for what it explicitly knows it is missing, rather than injecting massive chunks of context into the LLM and just hoping it can reason its way out.
And the empirical findings in the paper on efficiency are staggering. The researchers found that the system very rarely maxes out its search limits.
Really?
Yeah. In their testing, 95% of queries finished in just a single breadth step, meaning the very first logical decomposition was correct.
Wow.
Furthermore, they completed the entire verifiable proof in under 3 depth steps.
That is incredibly lean.
It really is. In fact, the total token cost, the amount of computational power required, is roughly equivalent to those older, flawed forward reasoning methods.
That's wild.
Systems using basic query reformulation or React burn through tokens because they retrieve massive, irrelevant text blocks and force the LLM to parse through all the noise.
Right.
Goal-Mem uses highly targeted surgical retrieval. It pulls up tiny, highly relevant facts and slots them into a pre-existing logical structure.
It is the difference between reading an entire encyclopedia cover to cover, hoping to stumble across a fact, versus opening the index, finding the exact coordinate, and turning straight to the page.
That's exactly it.
You are using the same book, but one method is vastly more efficient and far less prone to distraction.
And critically, vastly more accurate.
Well, the theory is beautiful, and the token efficiency makes it viable for real-world application, but, a perfectly logical framework is totally useless if it freezes up when dealing with actual human conversation.
True.
So how did Goal-Mem actually perform in multi-hop testing?
The researchers subjected Goal-Mem to rigorous benchmarking, most notably the Locomo benchmark.
Or Kamel.
Yeah, that's specifically designed to evaluate long-range multi-session memory. This is where the system has to navigate the sprawling, often messy reality of extended user interactions.
It's a true test.
The results represent a complete paradigm shift. For complex multi-hop questions, Goal-Mem delivered a massive 19% jump in accuracy over the baseline models.
Wait, 19%. A 19% improvement is almost unheard of in modern AI benchmarking. Research teams fight tooth and nail for a fractional percentage point.
I get
That
it.
is a fundamental leap in capability.
It is a leap enabled by the framework's versatility. Goal-Mem is entirely structure agnostic. Whether the underlying memory is stored as raw flat text, a complex knowledge graph, or a hierarchical tree. Layering Goal-Mem's backward chaining on top yielded substantial, consistent improvements across the board.
I want to highlight two specific anecdotes from the paper's testing data because they perfectly illustrate exactly why the older semantic models fail and how Goal-Mem succeeds in bridging those gaps.
Yeah, let's hear them.
The first is the story of James's puppy.
The location granularity problem. This is a classic failure point for semantic search.
Right, so in the testing data, the user asks the AI, in which state is the shelter from which James adopted the puppy? The older AI, using forward reasoning, tokenizes the prompt and searches the latent space for vectors related to James, adopted, puppy, and shelter. It successfully retrieves a memory that states James adopted a puppy from a shelter in Stamford.
And feeling confident in its semantic match, the baseline AI proudly outputs Stanford.
Which, of course, is a city, not a state.
Right. The forward reasoning AI finds a high lexical overlap, assumes its job is done, and regurgitates the local span of text. It has absolutely no conceptual understanding of the logical constraints of the user's question.
But Goal-Mem approaches the same prompt entirely differently. It begins by creating a subgoal that explicitly requires a variable of the type state.
Right.
It retrieves the memory about Stamford, but before it outputs an answer, it runs its type consistency check. The NL logic evaluates the retrieved entity and realizes Stamford is a city. The variable strictly requires a state.
So it rejects it.
Exactly. It rejects Stamford as the final answer and initiates a depth step. It uses its internal knowledge base to bridge the gap, recognizing that Stamford is located in Connecticut.
Brilliant. It unifies the retrieved memory with the logical requirement and correctly outputs Connecticut.
If we connect this to the bigger picture, it forces the system to build a structural bridge of verified facts. It refuses to hand you the first shiny semantic object it finds. It meticulously ensures the object actually fits the exact logical shape of your request.
The second example from the paper is even more subtle, and it demonstrates how Goal-Mem handles implicit context. It is the example of Jolene surfing.
Oh, this is a great one.
The user asks the system, "What outdoor activity did Jolene suggest doing together with Deborah?"
Okay.
The older semantic AI searches its memory database for variations of the phrase suggested outdoor activity. It fails to find a high-confidence vector match, assumes the event never occurred, and simply returns none.
Because semantic similarity is blind to missing logical steps. If the exact phrasing or a close synonym isn't present in the latent space, the model assumes the fact does not exist and gives up. But Goal-Mem doesn't give up. It realizes its first literal decomposition failed. This is where a breadth step comes into play.
Right.
It reformulates the goal logically rather than lexically. It expands the search parameter to ask, are there activities she is learning and wants to do with Deborah?
Pivoting to the intent.
Exactly. By pivoting to the underlying intent, it retrieves a memory where Jolene mentions taking surfing lessons and tells Deborah she should come with me. The AI evaluates the new evidence, correctly deduces that they were discussing an outdoor activity, and verifies the answer.
This highlights the core resilience of Goal-Mem. Semantic search shatters the moment you use an unexpected synonym or refer to an event obliquely or, span a single thought across multiple days of conversation.
Which is how we actually talk.
Right. By breaking the question down into logical requirements rather than lexical strings, the AI can successfully traverse the messy, informal ways that humans actually speak to one another.
It evaluates the underlying intent of the words rather than just mathematically matching the words themselves. And because every single step of that traversal is verified through unification, it entirely eliminates the hallucinations that plague systems trying to guess their way across complex multi-hop logic.
It won't tell you Jolene suggested skydiving just because the word sky happened to be in a nearby sentence.
Exactly. It requires verifiable proof.
Yeah.
So what does this all mean for the future of how you interact with these systems? Why does the shift toward backward chaining and natural language logic fundamentally matter to your daily workflow?
It's the big transition.
Right. It matters because this framework marks the definitive transition from AI operating as a search engine to AI operating as a true collaborator.
That distinction is the crux of the entire paper. A search engine is a tool that requires you to format your own mind to match the architecture of its database.
Wow.
But a true collaborator formats its understanding to match the architecture of your mind.
This research proves that your future AI agents won't just blindly retrieve the literal words you typed 6 months ago. They will logically map your
Yeah.
habits. They will follow the intricate threads of your long-term projects. They will connect the dots across entirely different facets of your life without needing constant, tedious reminders about context you have already provided.
It's seamless.
You won't have to say, remember when I told you I went to Momoko Cafe? And remember how I told you I prefer matcha flavors? You just ask the question naturally, and the system does the heavy lifting of connecting those disparate nodes into a logically verified answer.
It changes the fundamental texture of human-computer
It
interaction.
really does.
The dynamic moves from transactional retrieval to relational understanding. The AI begins to hold a persistent, coherent, logical model of who you are, what you prefer, and how you operate.
It means the AI finally gets to know you, not just as a bag of keywords you have accumulated over a year, but as a person with consistent, logically connected preferences.
This raises an important question, though.
Okay, what is it?
A rather profound one if we follow the trajectory of this verifiable reasoning. If an AI can now use backward chaining to perfectly map our past conversations, if it can hold thousands of these verified facts in its memory, flawlessly cross-reference them without fatigue, and logically deduce connections about our habits that we haven't even explicitly stated to ourselves,
Oh, wow.
at what point does an AI's logical understanding of our own behavioral patterns become more accurate than our own human self-awareness?
That is a remarkable paradigm shift.
Hmm.
We started this deep dive talking about the frustration of an assistant that acts like a friend who can't help you find your keys, frantically shouting out random rooms they heard you mention.
Yeah.
What Goal-Mem gives us is an assistant who not only knows exactly where you left them, but understands your routine so perfectly they logically deduce you will need them and remind you to grab them before you even realize you are about to leave the house.
Exactly.
Let that thought linger the next time your AI remembers something you thought was forgotten forever.